So today we're going to be looking at, we do have another z-test, but this time it's for a proportion. So now we're changing things up. So far with hypothesis testing, all we've looked at is the mean. That's all we've looked at. So now we're going to look at proportions today. So the proportion, same as a percentage of the population. Your hypothesis test involving a population proportion can also be considered a binomial experiment when, and these are just some of the same properties from our binomial experiment when we talked about those way back in like chapter 4 or 5. So there's only two outcomes. The probability of success does not change from trial to trial. So it's just a binomial experiment. We're not talking a full-out binomial distribution type deal yet. The assumptions for our z-test for a proportion: our sample's random. Condition 2, the conditions for the binomial experiment are satisfied. For number 2, we've talked about those binomial experiment conditions several times. I would not take the time at this point to rewrite those down again. Just wanted to refresh those with you. We have a fixed number of trials. Each trial only has 2 outcomes, or if you have multiple outcomes, you can group them or simplify them down to 2 outcomes. Outcomes for each trial are independent, and the probability of success is the same for each trial. Again, I would not take the time to rewrite those properties. Again, we've seen them at least 3 other times. N times P and N times Q have to be greater than or equal to 5. And remember, P is just our probability of success. Q would be our probability of failure. N is just our sample size. So sample size times each probability, or in this case we are talking proportions. So sample size times each proportion needs to be greater than or equal to 5. Our formula for our z-test, it is a little different now. I know the formula when we tested the mean for the z-test or t-test, the formulas were essentially the same. One involved population standard deviation, one involved sample standard deviation. That was the only difference between the two. Now for our proportions though, we were introduced to this with our confidence intervals. It's our p hat. And it's just our sample proportion. Our capital X, remember, is just how many successes we have, or how many objects in our sample have the characteristic we are interested in. Just the plain old P, no hat on it, is just population proportion. N is your sample size. And once again, to get Q, just 1 minus P. Or you could also make the side note too, P plus Q equals 1. Sorry, guys. Alright, so let's try this out. We're already really familiar with the z-test for the mean. So now the z-test for the proportion, there's just only a couple differences for us. The 5 steps are the same. Take a little read through example 1. The percentage of physicians who are women is 27.9%. In a survey of physicians employed by a large university health system, 45 of 120 randomly selected physicians are women. Is there sufficient evidence at the 0.05 level of significance to conclude that the proportion of women physicians at the university health system exceeds 27.9? Steps are not going to change, but before you really dig in, you might want to go ahead and decide, are you going to do traditional method or p-value method? We talked a little bit about that yesterday. If it doesn't specifically say p-value, I want you to do the traditional method. So if it doesn't specifically say p-value, do traditional. Either way, p-value or traditional, step 1 is state your hypotheses and identify your claim. Now, I know some of us right now, we're busy writing and we probably have some H's and we probably put a mu after them. because that's what we're used to, and that's all we've done so far. But I'm not going to have a mu in my hypotheses. What will I now have? Now I'm going to have p. In the null hypothesis, guys, you're still going to have your equals. The symbol has changed. And some of you are giving me confused looks like, wait, whoa, where'd that goofy M looking thing go? We're dealing with proportions in this case. So I know come test time, it has to be, I have to know when to use each thing and how to use it. So when I pick out the keyword proportion, now in my hypotheses, I'm dealing with lowercase p, no longer the mu. And we have, they're hypothesizing that the percentage is 27.9. Remember, we need to change that from our work with proportions last unit. We need to change that back to a decimal from a percent. What are we interested in? We're looking at that the number of women physicians exceeds that 27.9%. So if it's going to exceed it, we want to be greater than it. And since this researcher is interested in the exceed part, that's what they're trying to show, that alternative hypothesis is our claim. That's what we're trying to show. So very, very similar to the hypothesis testing we've done with the means, we have a different symbol now. Step 2, we're doing traditional methods, so step 2, we still want to find critical values. I always like to just pull from the question. I jot down my alpha level, my significance level, and I always like to write myself a little note, what type of test am I dealing with? Two tail, left tail, or right tail? Just helps me draw my sketch. Alternative hypothesis, that symbol is pointing to the right, so we're going to have a right-tailed test. If it helps you to draw your sketch at this point, you can. We have a z-test, so we just have that standard normal distribution. The right tail is shaded. And we talked about this when we did our first z-test for the mean. We talked about finding that critical value if we have the right tail. Remember, whether you're using the calculator or the table, you have to know the area to the left. So we need to do the 1 minus your alpha value. Or I know some of you have done the shortcut where you use the 0.05 and then you take that negative z value and you just make it positive for the right side. You can do either way you want. At this point, you should have an idea of how you find those critical values best. Table or calculator, and then do you do the 1 minus and use that area? Or do you just keep the area and take the negative off of the z? Totally your choice on what you want to do at this point. This one comes out to be, and this is one of those, if you do the calculator, you're going to get a 1.64. If you use the table in the book, you get 1.65. That 1/100th is not going to make or break us on this. So either way is okay. So if you did the calculator and 1.64, totally fine. So we have our critical value. Up next is our test value. So we do have a new formula. In order to use our formula, we need p hat. We need p. And we need q. And n. Those are the pieces I need for our formula. I like to just make that little list before I substitute in, especially distinguishing. What helps me the most, why I do this, is because in the formula you have p hat and you have p. I like writing them down and labeling them so when I go to substitute in, I don't get those two goofed up. I see them labeled. That helps me a lot. So the p hat, that's the information coming from the sample. That's our 45. That's our 45 out of 120. That's our p hat. Now, if it works out, double check. If it works out to be a nice decimal, go with the decimal. Those are much easier to do our computation with. Does this one work out nice? What do we got? 0.375. Use it. If you want to figure out maybe a simplified fraction, you can. If you want to use the fraction, you can. But to be honest, decimals are way easier to plug and chug with, I think. All right, so then the p without the hat, just plain old p, that's what we hypothesized our proportion to be. That's our 0.279. That's our 27.9%. Oh, that's a 2. It looks like a 1. There we go. Q then, to find Q, remember, just do 1 minus your p-value. And that's been a common theme for us. P and Q, those ideas, those are not new ideas for us. And then I need my sample size. And we had 120 physicians that were selected. Do you have to make the list? No, all this information, with the exception of the specific Q value, it's all in the information presented and given to you in the problem. I like to make the list because there's two very similar variables. There's p hat and there's p. I like to write them out, label them, so I substitute and write. All right, I know you guys have the formula in front of you there in your outline, I'm hoping. But if you don't, here we go. Z equals sample proportion minus population proportion, our hypothesized one, divided by, and again, everything in the denominator is underneath that radical. I know it's a little bit different for us. We're used to just our sample size being under there. But we have P, not P hat. We have P times Q divided by our sample size. So just take a minute, double check, and double check me. When I did this, I got roughly 2.34. So just take a minute, enter it in, make sure you're matching. Now at this point, we're approaching step 4. Step 4 is reject or not reject. That is our question. 2.34 is going to be somewhere further this way. And again, my pictures are never perfect. Our test value of 2.34 ends up in that shaded region. Shaded region equals rejection region. I reject, and you can just put the H sub 0. You can write null hypothesis if you'd like. I just like to shorthand it. Reject H sub 0. That's our null hypothesis. So if I rejected this, if I rejected the null hypothesis, and it wasn't my claim, that means I get to support my claim. If I reject the null, that means I get to support my claim. So step 5, we get to say there is enough evidence to support the claim that the proportion of women physicians exceeds 27.9%. And yes, that summary statement, that is important. Remember, we're not proving anything. The only way we could prove something is if we had all the information about our specific population. We don't get to prove it. Based on the evidence, based on the data from our sample, that evidence gives us enough to actually support our claim. We get to support. So if you take a look through, the 5 steps are the same as when we did our traditional method for the mean, for z-test or a t-test. The steps are the same. I state my hypotheses, identify my claim. The new thing for step 1 is now our symbol is p instead of mu, because we switched from proportion to mean. Step 2, finding the critical values, find them the same way as we did our z-test for our mean. Same thing, so that part isn't new. Step 3 is still finding our test value. The formula has changed, yes, but the actual step of finding the test value has not. It's still step 3. Different formula. All the pieces, though, we're very familiar with from our confidence intervals. Step 4, how we decide to reject or not, that has not changed. That's the same as z-test for the mean. And step 5, how we summarize, that beginning of that statement hasn't changed either. So a lot of very, very similar things. So I know some of you are like, Miss Golly, I'm still trying to wrap up 8.3 and we're moving on to 8.4. It's the same stuff though. It's the same idea. So speaking of the same idea, I did want to make sure I did one more example today that did have us do the p-value method. I think that's the method that makes most of us kind of the most nervous, especially if you're a table person instead of a calculator person. If you're a calculator person, you probably don't have a preference really either way of which one you do. So if we take a quick read through the question, we have an Energy Information Administration reported 51.7% of homes in the U.S. were heated by natural gas. Random sample of 200 homes found 115 were heated by natural gas. Does the evidence support the claim or has the percentage changed? Alpha is going to be 0.05, and here it specifically says p-value method. I know some of you, when I asked the question, the last one, what method are we going to use? Some of you are like, I'm not sure, it doesn't say. If I want p-value, I will specifically tell you p-value. Hypotheses, still step 1, no matter which method you're using. How do I know the symbol? How do I know the symbol? So we have, I know it doesn't specifically say proportion in here, but what does it talk about? Percentages. This question does not specifically say the proportion of homes heated by natural gas. It talks about the percentage. So we need to make sure we can make that connection between the two. Percentage, proportion, we're going to have the P for our symbol. The null hypothesis always has the equal to, and it's reported. The reported one is the 51.7%. Again, changed to a decimal. And so that's the thing we're actually claiming, is that it's 51.7%. It doesn't say anywhere in the question, some of us kind of struggle if it doesn't specifically say it has increased, decreased, things like that. If those statements are missing, that's when we have our two-tailed test. Now it wants to know, does the evidence support the claim? What they're trying to claim is that 51.7% of homes are heated by natural gas. That's what they're trying to claim. So that it is actually the 51.7%, your claim is your null hypothesis. So again, be very careful. I know some of us, we kind of get in the habit of we try to memorize, oh, the claim's going to be the alternative. It's not always the case. More times than not it is, but it's not always the case. We have to see what the specific researcher is interested in. All right, since we're doing p-value method, step 2 is no longer critical values. Some people really grow to like p-value method because you don't have to find critical values. Step 2 is your test value. So to find the test value, I'm going to go ahead and make my list of necessary information. I'll go in the same order as last time. And we need N. P hat is what comes from our sample. So 115 out of 200. Does that give us a nice decimal again? Did anybody do that? 0.575. Sweet, nice decimal. I like those. 0.575. Then P, remember, is our hypothesized proportion, or percent. Q, we do 1 minus. And then our sample size, in this case, we had 200 homes. Making that list, listing those things out, I know some of you are like, Miss Golly, it says all that in the question. Except for Q, we do have to do a little work for Q. Again, I like to list it out to help me make sure I'm accurate when I find that test value. For our formula, we do p hat minus p divided by huge radical, or square root, whichever you like, p times q divided by our sample size of 200. Do a little plugging and chugging. Get roughly 1.64-ish if you want to try that out. Feel free. You should get roughly 1.64. Now I do want to show you how to find the p-value. If you're a table person, I know I still have a mix out there, so I want to make sure I show both. Our z-test value was positive 1.64, so we'd be over on the right side of the table. See if it'll let me do a quick sketch here. There we go. So I'm looking for, here's 1.6, 1.64. Remember, your p-value represents P for probability. Probabilities are represented by areas under our curve. So I take my test value and I find the area that corresponds to it. And I know that's very small for you guys to read. It's 0.9495. Two-tailed test, I have to double. I have to double since it's a two-tailed test. I'm going to have to double it. But before I do that, though, this gives me the area to the left. So we do have to do, since it's a positive and it gives me the area to the left, here's where it gets a little goofy for p-value, and this is why I really like the calculator too. The area we haven't had to deal with this one yet when we've done p-value. Our test value has ended up to be negative, at least all the examples I've done with you. So when you have the area to the left of a positive z-test value, to get your p-value, you do have to subtract that area from 1. And I know we haven't done one like this together. That's why I chose the example. And then since it's two-tailed, you do have to double it. So again, the reason why we had to subtract from 1, our z-test value ended up to be positive. It ended up over here on the right. When I look that up in the table, it's not giving me the area in the tail, which would be over here. It's not giving me the area in the tail. It's giving me the area to the left. I need the area in the tail. So I have to do 1 minus the area given to me in the table. If it were just a right-tailed test, I would leave it. That's my p-value. Since it's a two-tailed test, I have to double that area. So then to reject or not, I will show you guys the calculator stuff for this. So this area is 0.10. Sorry, it's two-tail. So I guess split it. All right, so then our alpha value, what was it? 0.05. So that has to be split amongst the two tails. So alpha would be 0.025. So our p-value is in the red. It is bigger than our alpha value. P-value greater than alpha, so we do not reject. Do you have to draw out that sketch? No. I know for some of us, when we do the areas, it's tougher to draw the sketch. Again, the p-value area, I did have to split it back up between the two tails. The p-value is in red. It's a larger area, so it's going to be a bigger tail piece shaded than the alpha. The alpha is only at 0.025. That's in the green. So the p-value area is greater than alpha. When the area for the p-value is greater than the area for alpha, that's when we do not reject. Or if you are more of a memorizer person, you want to draw the sketch, p-value is greater than alpha, you don't reject. P-value is less than or equal to alpha, you do reject. So it's just two different cases possible. Now, we didn't reject this, and it's our claim. So there is not enough evidence to reject the claim that, and I'm running out of space. The claim that, and all I can do is etc. I'm out of space up here, but it'd be the claim that the percent of homes heated by natural gas is 51.7%, or something along those lines. You just have to restate your claim. I'm out of space at the bottom. I run into my little toolbar down there. So the claim that 51.7% of homes in the United States are heated by natural gas. That would be how you just rephrase your claim. Now, the calculator piece, there is a calculator test for this, same as we've had for the last couple. And I'll be very honest, when it comes to p-value, I think it's easier to use the calculator stuff than having to try to remember, okay, now I looked up the area. Since it's the area to the left, I have to subtract it from 1. To me, the p-value can get pretty involved. So, let's show calculator. Maybe. There we go. And calculator steps are also on page 459. We go to stat. Hang on, mine's not working for some reason. And we arrow over to tests. Item number 1. So in case you were doing the z-test for the mean or the t-test for the mean, and you were doing everything with a table and things, and you're thinking, oh, maybe that calculator isn't such a bad deal. Maybe I should start trying that out. So just to refresh you, number 1, the z-test, that's a z-test for the mean. That's what we did in section 8.2, if you want me to link it up that way for you. Number 2 up there is the t-test for the mean. That's what we did in section 8.3. The item we need, though, and it would be nice if it just went 1, 2, 3 for us, but it doesn't. We need option 5. It's a one proportion z-test. We're only hypothesizing about one specific proportion. We're not comparing two. It's just a one proportion z-test. Still a z-test. It's just the one proportion z-test. So p sub 0, that's what you're hypothesizing your population proportion to be. So I'm just going to look at this for the very last example, 0.517. The x that you're putting in, that's how many successes you had in your sample, or how many items in your sample fulfill the characteristic that you're interested in. We are interested in homes being heated by natural gas. So in our sample, there were 115 of those. And then n is your sample size. And we had a two-tailed test. We go to calculate. We get, oh, thank you. I was wondering why I was so far off. Thank you. Yes, if you were copying mine, I did have a typo there. I put in 120 instead of 200. That's very strange. There we go. All right, let's try that again. I was wondering why my numbers looked really goofy. All right, so there we go. So we see we have a z value. That is your test value. So take a look at what we did in step 2. We got 1.64. Calculator gives you 1.64. The only thing I caution you with the calculator, if I ask you for the traditional method, this is your test value, not your critical value. Critical value, you still have to find those for the traditional method. I really think the calculator, to be honest, it cuts down on the busy work of the formula for the test value, and it also cuts down on any kind of confusion you have for the p-value. Do I have to do the 1 minus thing? Do I have to double it? How do I get my p-value? If you use the program in the calculator, it gives you the p-value. It's done. You don't have to double it. You don't have to subtract it from 1 and then double it. It's done for you. So it's up to you what you want to use. I just want to make sure you were aware of this. And then also remind you, for the last couple tests we've done, they are options 1 and 2 on the same menu. So if you're nervous about, well, what if I forget where to go on the test? If you do the practice questions I assign you, and I think this one has, I don't know, maybe like 8 questions or something like that. If you use that same program 8 times, chances are you're not going to have a problem remembering where to go come test time. But if you don't do any of the practice with it, yeah, you might kind of forget about it come test time. So if you want, try the calculator as you do your practice. That's my big suggestion for you.